In the last video, we have seen the deciding factors of the strength of acid and base. Now here I'm going to explain how the strength of the acids and bases can be quantified. How can we get a value for the strength of acid and base, and so that we can compare the acidic strength and basic strength of different compounds. Now that is done using dissociation constant, or we can even call it as ionization constant. Now we know that acids ionize, bases ionize, and it is based on their ionizing capacity that we decide whether it is a strong acid or a weak acid, or a strong base or a weak base. Now this capacity can be quantified, and that is done using dissociation constant or ionization constant. Now let us take the example of a weak acid. Okay, now consider a weak acid HA. It will be ionizing in water to form H3O plus and A minus, that is the H plus ion will be taken up by H2O and it will form H3O plus, and A minus ion will be available, the anion. So this since it's a weak acid, it will be incompletely dissociated. Now initially the concentration of HA will be C moles per liter, and that of the H3O plus and A minus will be 0 moles per liter. Nothing will be ionized first, initially, in the beginning. At equilibrium, what happens? Some amount of acid would have ionized, and when the equilibrium reaches, the concentration of HA will be C minus C alpha, and that of H3O plus will be C alpha and A minus will be C alpha. Moles per liter, the concentration. That means C alpha amount of HA would have ionized to form H3O plus and A minus. So the concentration of HA will be decreased to C minus C alpha. Now using this, we can write the ionization constant or the dissociation constant of HA. That is the ionization constant Ka is equal to H3O plus, concentration of H3O plus, into concentration of A minus divided by concentration of HA at equilibrium. So what was the concentration at equilibrium for these terms, these ions or these species? We substitute that in this equation and we get it as C alpha square by 1 minus alpha. That is, C alpha is the concentration of H3O plus and A minus, that we put it in the numerator, and C minus C alpha is the concentration of HA at equilibrium. C minus C alpha can be put it as C into 1 minus alpha, and that C and 1C in the numerator and denominator get cancelled, and you get Ka is equal to, the ionization constant is equal to C alpha square divided by 1 minus alpha. Now, smaller the value of Ka, weaker will be the acid. So if you have different acids with different Ka, you can compare the ionization constant value and predict its acidity. So whichever has got high Ka value, that will be stronger acid. Whichever has got small Ka value, that will be a weaker acid. Now another term which we can introduce over here is a pKa. pKa is nothing but negative log of Ka, like our pH. Okay, so greater the pKa, weaker will be the acid. Okay, larger the value of pKa, weaker will be the acid, or smaller the value of Ka, weaker will be the acid. Now we can even simplify this equation Ka. We have Ka equal to C alpha square divided by 1 minus alpha. Now for weak acid, since it is incompletely ionized, alpha, the degree of ionization alpha, will be very less or than 1, comparatively very less than 1. And so you can eliminate this 1 minus alpha term. So alpha is very much less than 1, so denominator becomes 1, and so our Ka will be equal to C alpha square. Or you can bring this down into alpha, that is the dissociation constant, or degree of dissociation, equal to root of Ka by C. So alpha is the degree of dissociation, that is the extent to which the acid has dissociated, or it is alpha is the fraction of the total number of moles of acid which has been dissociated at equilibrium. So you can calculate the degree of dissociation of an acid, weak acid, using the term alpha equal to root of Ka by C, where Ka is the dissociation constant of the acid, and C is the concentration, initial concentration of the acid. Remember, Ka for acid will be constant. Every acid has got its own Ka value. Alright, from this we can even calculate the pH value, that is the concentration of H3O plus can be calculated, from which we can calculate the pH. Concentration of H3O plus will be equal to C alpha. We have here it is. Okay, so we can calculate H3O plus value also. So this is the dissociation constant for, degree of dissociation for weak acid. Now from this we can compare the acidity of weak acids, that is the relative strength of weak acids can be known. So suppose we have two weak acids, Ha1 and Ha2, with the dissociation constant Ka1 and Ka2 and degree of dissociation alpha 1 and alpha 2. Then alpha 1 will be equal to root Ka1 by C and alpha 2 will be equal to root Ka2 by C. So we are assuming that the concentration of these two acids are the same. Then we can compare the strength of these two acids. The ratio for the strength of Ha1 to Ha2 will be equal to alpha 1, degree of dissociation of 1 by degree of dissociation of 2, which is equal to root of dissociation constant of 1 divided by dissociation constant of 2. So this is the equation for the relative strength of weak acids. The way we have found the ionization constant and degree of dissociation for weak acid, we can find an expression for degree of dissociation for a weak base. Now let's consider a weak base BOH. So it will incompletely dissociate to B plus and OH minus. Let the initial concentration of the base be C moles per liter, and that of B plus and OH minus will be 0 initially because no ionization will happen. At equilibrium, if alpha is the degree of dissociation, then the concentration of BOH will be C minus C alpha, and C alpha and C alpha, the concentration of B plus and OH minus will be C alpha. That much amount of ionization would have happened. And we can get the ionization constant of BOH, Kb, equal to B plus into OH minus divided by BOH, concentration terms of the ions divided by concentration term of the base. Now we put into the concentration terms of the base and the ions, then we get Kb will be equal to C alpha square divided by 1 minus alpha. And smaller the value of Kb, weaker will be the base. If we put it in terms of pKb, larger the pKb value, weaker will be the base, same as that of the acid. Now we have the expression pKb equal to C alpha square divided by 1 minus alpha. Alright, and we can assume that, we can say that since alpha, the degree of dissociation will be very less than 1 for weak base, alpha will be very, very less than 1. So the denominator term in this equation will disappear, or it will be 1. So Kb will be equal to C alpha square, or the degree of dissociation alpha will be equal to root of Kb by C. For acid, it was root of Ka by C. Alright, so this is the degree of expression for degree of dissociation for a weak base. So concentration of OH minus can be brought from C alpha, the value C alpha. Now when we compare the strength of the bases, the way we had done for acids, let's consider two bases BOH1 and BOH2 with the ionization constant Kb1 and Kb2 and degree of dissociation alpha 1 and alpha 2, then their degree of dissociation alpha 1 will be equal to root of Kb1 by C, and that of alpha 2 will be equal to root of Kb2 by C, and the relative strength of these two bases will be root of Kb1 by Kb2. Alright, so this is the this is the way by which we can compare quantitatively the strength of bases, same way we have done for acids. Now let us look into the relation between the Kb of a base and Ka of its conjugate acid. Okay, that is ionization constant of a base and ionization constant of its conjugate acid. Let us take the example of a base B, which will ionize to BH plus and OH minus ion in the presence of H2O. So B is the base, H2O is the acid. BH plus will be the conjugate acid of B, and OH minus will be the conjugate acid of base of H2O. Alright, so ionization constant of B will be equal to Kb equal to BH plus into OH minus by concentration of B. And when we we'll do a sort of mathematical treatment over here. Okay, multiply both numerator and denominator by H3O plus, that is hydronium ion. Alright, we get this expression. This plus will be what we call the superscripts. Okay. Now we'll rearrange this equation. Then you bring this OH minus and H3O plus to one side. You get OH minus into H3O plus into BH plus by B into H3O plus. Now we know that the product of hydroxyl ion and hydronium ion is nothing but the ionic product of water. Alright, so this is Kw. This first term will be Kw. So you get, we can consider this as Kw into BH plus by B into H3O plus. Now, let's consider the ionization of the conjugate acid BH plus. Okay, H2O will be the base. H2 will abstract proton, it will form B plus H3O plus. And ionization constant of BH plus will be Ka equal to B into H3O plus into BH plus. Put equation 3 into equation 2. So when you compare equation 3 and equation 2, you find that they are reciprocals. So you can put here in equation 2, Kb equal to OH minus into H3O plus divided by Ka. Okay, this will be 1 by Ka. Now the OH minus and H3O plus is nothing but Kw. So Kb will be equal to Kw by Ka, or Kw equal to Ka into Kb. Alright, so that means the ionization constant of the conjugate acid and ionization constant of the base, the product of these two ionization constant will be equal to the ionic product of water. Now that's very important. So if we know the ionization product of ionization constant of base, we can easily calculate the ionization constant of its conjugate acid. Alright, and vice versa. So you can say that in terms of pKw will be equal to pKa plus pKb. Okay, in terms of P negative logs. And we know that pKw is 14. Okay, and Kw is nothing but equal to 10 raised to minus 14. So from this we can easily calculate the Kb or Ka of the acid and base, conjugate acid base pair. Now that's the beauty of this expression. Alright. So we have seen about the dissociation constant of weak acid and base. Now let us look at the dissociation constant for a polybasic acid. Now polybasic acids are those acids which has got more than one ionizable proton per molecule, like our H2SO4, H3PO4, etc. That is sulfuric acid, phosphoric acid, etc. Now they are also called as polyprotic acid. Now if there are two ionizable protons, then they are called dibasic acids. Like H2SO4 is a dibasic acid. So just a general expression for the ionization of dibasic acid H2A. Okay, H2A with in the presence of water will ionize to H3O plus and HA minus. And its ionization constant Ka1 can be written as a product of H3O plus into HA minus divided by H2A. Now we put it as Ka1 because it is called the first ionization constant. Now one proton has been lost, we have got another ionizable proton on HA minus. Now that ionization can be written in this way. Okay, HA minus plus H2O giving H3O plus A2 minus. And its ionization constant Ka2 can be written in this way: H3 concentration of proton H3O plus into concentration of A2 minus divided by concentration of Ha minus. So you've got the first ionization constant and second ionization constant for a dibasic acid. So for a tribasic acid, you will have first, second, and third ionization constants. All right. Now, say you have this phosphoric acid. It has got Ka1, Ka2, Ka3. You can see here when you observe the ionization constants of phosphoric acid, the ionization constant decreases as we go down. That is, by the time it reaches the third ionization constant, it has got very low value. Now, what does this implicate? What does this indicate? Now, that means as you, that is the higher order dissociation constant are smaller and lower order dissociation constants are having higher value. So this is for polybasic acids. Now, this is because it becomes difficult to remove a proton from a cation. See, when the first ionization was happening, it was H3PO4, which was a neutral compound. Now, in the second case, in the second ionization, you are releasing a proton, you are ionizing a proton from H2PO4 minus, an anion, a negatively charged ion. So, removal of a proton from a negatively charged species becomes difficult. That's why its second ionization constant is low. And when you come to the third ionization constant, you have got two negative charges on HPO42 minus. So removal of a proton from a more negative ion becomes more difficult. So the higher order dissociation constants are having lower values. Alright, so it becomes difficult to remove a proton from HPO42 minus, and then from H2PO4 minus, and then from the H3PO4 minus comparatively easier to be removed, proton easily to be removed. So the order is Ka1 will be having greater value than Ka2 will be having greater value than Ka3. Now the overall dissociation constant of this compound, this acid, will be the product of Ka1, Ka2 and Ka3. That is, Ka will be equal to, or K will be equal to Ka1 into Ka2 into Ka3. So for any polybasic acid, the overall ionization constant or dissociation constant will be the product of the different various first ionization, second ionization, third ionization, etc. And remember, the higher order ionization constants are having lower value. That's because it becomes difficult to remove a proton from a negatively charged species. Alright, so that's regarding the ionization or dissociation of acids and bases. Thank you.